Hello, welcome to the course JPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Kleppner and Kolenko. We will continue to discuss topics from Chapter 4, Work and Energy. In the last class, we have seen, in the case of motion in several dimensions, how we integrate the equation of motion with respect to position. Okay. So at the end of that procedure, we got a result like this. So a particle was moving from an initial position A, characterized by position vector Ra, with the corresponding velocity is Va, and at the end of the motion, it reaches the final position B, characterized by position vector Rb and velocity Vb. And if the motion happens under the influence of a force F, then integral over Ra to Rb F dot dr equal to half mvb square minus half mva square. So if you look at the equation, the left hand side is nothing but the work done by the force in moving the particle from A to B. You call this as WBA. And half mvb square, this is the kinetic energy at the end position B, called this as kb, and half mva square, this is the kinetic energy at the starting position A, called this as ka, and once again you get wba equal to kb minus ka. So the net work done by the forces on an object equals the change in its kinetic energy. So this is work energy theorem in several dimensions. So if you recollect what we have done in the previous class, so we have a net displacement happening from initial position A to final position B. So we have divided this into a number of finite segments. In each segment you assume that the displacement is delta R. Then you calculate the work done by the force F in that small segment. You call it as delta W. So delta W is going to be F dot delta R. So you imagine that theta is the angle between the force and the displacement. Then you can expand the dot product. You write it as F cos theta delta R. And as you can see, the force in an arbitrary direction, you can dissolve this into a parallel component and a perpendicular component, and F cos theta is going to be the parallel component, the component of force in the direction of the displacement. So you call it as F parallel delta R. So for a finite displacement from Ra to Rb, the work on the particle integral A to B F dot dr is nothing but the sum of individual contributions delta W equal to F parallel delta R from each segment of the path. And in the limit where the size of each segment approaches 0, in other words, number of segments become infinity, then you have an infinite summation, and the infinite summation can be approximated to an integral. So this is what we have done in the previous class. Now, as the statement suggests, the work is done, need not be done by a single force. It could be a combination of forces. In such cases, the net force is a sum of individual forces. So you can write F equal to sum over I, Fi. So your expression for work done becomes WBA equal to integral over I, WIBA. And according to work energy theorem, this is going to be final kinetic energy Kb minus initial kinetic energy Ka, where Wi Ba is nothing but the work done by the ith force on the particle. So this is the case of a single particle. What happens if you have a multi-particle system or an extended system? We have seen in the previous chapter that in such cases, the equation of motion is given by the center of mass, right? So there you write F is equal to mr double dot, where capital R is the position vector of the center of mass. So in terms of velocity, I can rewrite this as F equal to m into dv by dt, where capital V is the velocity of the center of mass. Now if you follow the same procedure, that is integrating this with respect to position, then once again you get the work energy theorem. So here integral Ra to Rb f dot dr equal to half m capital VB square minus half m capital VA square. So this is the work energy theorem for the translation motion of an extended system. Now, what is the significance of this work energy theorem? As I said in the previous class, in some cases, without solving the equation of motion, we can derive a lot of important information or a lot of physical insights about the system under study using the work energy theorem. Let's take one example of a conical pendulum. In the previous chapter, we have analyzed conical pendulum in detail. We know how to write down the equation of motion and also how to write down the constraint equation using the length of the rod as the constraint parameter. And we know how to solve this and get the trajectory. Okay. Now what we are going to do now is, we are not doing a detailed mathematical analysis. We will see how by applying the work energy theorem we can get some very important information regarding the motion of conical pendulum. So if you recollect, conical pendulum consists of a mass m which hangs by a massless rod of length L. And the mass rotates with a constant angular velocity omega about the center point. Now the mass moves in a circular path of constant radius r, and the radius is constrained by the length of the rod. And the forces acting on the mass are the tension which acts along the rod in the upward direction and the weight which acts vertically in the downward direction. Now if you look at the work done by these two forces, actually these two works are at zero, because if you look at the direction at this particular point, the dr, the displacement is along the tangential direction, and if you look at tension and displacement, these two are perpendicular to each other, right? So when you calculate f dot dr, so t dot dr, dot product of two perpendicular vectors is 0, so work done by the tension is 0. Same way, if you look at dr and w, these two are also perpendicular to each other, so work done by the weight is also 0. So in other words, the work done by all the forces is 0 in this case. So if you look at this equation of work energy theorem, the left hand side is 0. The net work done by the forces on the object, this is 0, which means the right hand side, that is the change in kinetic energy, has to be 0. When the change in kinetic energy is 0, you can say that the kinetic energy is a constant. So mathematically, what does this mean? We know that kinetic energy is half mv square. Since we are talking about circular motion, the linear velocity v I can write in terms of circular velocity or angular velocity omega as v equal to r omega. So k equal to half mr square omega square. We have said in the beginning that the angular velocity is constant. Since this is circular motion, the radius is also constant, so kinetic energy is a constant. Okay. So without actually solving the equation of motion, we have shown that the kinetic energy is conserved by simply applying the work energy principle. Same way, we can also analyze the case of escape velocity in the general scenario. In the last class, we have discussed the one-dimensional motion of a mass m projected vertically upward from the surface of Earth. And we have found that if the initial speed is less than the escape velocity, then the object will come back to the surface of Earth, pulled down by the gravitational field. On the other hand, if the initial velocity is greater than the escape velocity given by square root of 2g re, where capital Re is the radius of Earth, then the mass will be able to escape the gravitational field of Earth permanently. So this is the case of vertical motion. Let's look at a more general scenario, that is the object is projected at an arbitrary angle alpha with respect to the vertical. Okay. So for ease of analysis, let's once again imagine that the air resistance is negligible. So the only force acting on the object is the gravitational force given by F is equal to minus gm by r square r cap, where capital M is the mass of Earth and small m is the mass of the object. Okay. We know that the acceleration due to gravity small g is gme by ra square. So we can rewrite this equation in terms of acceleration due to gravity as minus mg ra square by r square r cap. Now when you want to calculate f dot dr, we know f now. Now we need to calculate what is dr, or the displacement. So this is some kind of a rotational motion or a circular motion, right? So we can invoke the polar coordinates here. So there are two types of polar coordinates: the spherical polar coordinates, where the coordinates are r, theta and phi, and you also have the cylindrical polar coordinates, where the coordinates are r, theta and z. For now, let's limit our analysis to the two-dimensional case. So basically you need to deal with only two coordinates, r and theta. So let's now calculate the displacement vector dr in terms of r and theta. So when you have a circular motion, r is nothing but the radius and theta is the angle. Okay. Now, what is the displacement in the direction of r? So just like an infinitesimal displacement in the direction of x is dx, an infinitesimal displacement in the direction of r is going to be dr along the same direction. Now what is the length component corresponding to the angle theta? So we know that the angular displacement is d theta. So if this is d theta and this length is r, then we know that this length is going to be r d theta. So the length component corresponding to theta is nothing but r d theta. So now you can define your displacement vector dr as dr r cap plus r d theta theta cap, where r cap and theta cap, just like x cap and y cap, or I cap and j cap, these are unit vectors. So r cap is along the direction of r and theta cap is in the tangential direction. Okay. So once you know f and dr, now we can calculate f dot dr. This is going to be minus mgra square by r square dr. Now you can put this into the work energy theorem expression. So half mv square minus half mv naught square, where v naught is the initial velocity with which you are launching the object and v is the final velocity. This is going to be integral over f dot dr. So here mg r square, all these are constants, so you take it outside the integral. So integral re to r dr by r square. So lower limit is nothing but the radius of Earth, because you are launching the object from the surface, and r is the final position of the object. Integral of 1 over r square is minus 1 by r. So when you apply the limits, you get this expression. Now how do we calculate the escape velocity? So we need to apply some limiting, we need to apply some boundary conditions. We know that when the object reaches the maximum height, the velocity is going to be 0. So at r max, v equal to 0. So this term gets vanished. Now in the case of escape velocity, the object can go far away from the surface of Earth. So for all practical purpose, you can equate r max to infinity. So when you make these two changes in your equation, that is r equated to infinity and v equated to 0, you get the expression for the escape velocity v naught as square root of 2gr, so which is going to be 1.1 into 10 to the power 4 meter per second. So once again, just like the case of one-dimensional motion, here also the value of escape velocity is a constant. So we have shown that escape velocity is independent of the launch direction, because the angle alpha doesn't feature anywhere in the final expression. One thing you have to keep in mind is that during our analysis we have neglected the Earth's rotation. So in the absence of air resistance, the projectile should be fired horizontally to the east, since the rotational speed of Earth's surface is then added to the launch velocity. On the other hand, if you fire it in the west direction, what happens is the rotational speed of Earth is going to act against your launch velocity. So in that case, you will have to launch it with an initial velocity which is slightly higher than this value. Only then the object will be able to break the gravitational field of Earth. So we have seen in the case of one-dimensional motion and motion in several dimensions how to derive the work energy theorem. Now the real question is, how are we going to apply this into a practical system? So if you recall the procedure, we have first taken the Newton's second law, then integrated it with respect to position, and that's how we derived the work energy principle, right? So we haven't introduced any new physical ideas, we just follow some simple mathematics. Now one thing you have to remember is that to apply the work energy theorem to a practical system, we have to evaluate the line integral for work, right? Because the left hand side, WBA, is nothing but integral A to B F dot dr. The problem is that this line integral depends on the path from A to B. So if you want to calculate the value of this line integral, we need to know the path from A to B. Now this is going to be a problem. How do you know the path, or how do you know the trajectory? To know the trajectory, you need to solve the equation of motion, then you get position as a function of time. That's how we come to know about the trajectory, right? And without knowing the trajectory, apparently we cannot apply the work energy theorem. So when I introduced work energy theorem, I said the utility of work energy theorem is that without solving the equation of motion, we will be able to get some useful information about the system under study. But now it appears that without solving the equation of motion, you cannot actually apply the work energy theorem. So it looks like work energy theorem is superfluous, or it's redundant, right? Because once you are able to solve the tedious equation of motion, then using that equation of motion, you can get all the important information regarding the system. You don't need an extra theorem like work energy theorem. So does this mean that work energy theorem is completely useless? In general, the work integral depends on the path followed, and since we don't know the path without completely solving the problem, the work energy theorem is useless. But this is not the entire story. There are fortunately two special cases of considerable practical importance. First one in the case of conservative forces. So in the case of conservative forces, the work integral does not depend on the particular path, it only depends on the end point. So in the case of conservative forces, you can apply work energy theorem, and without solving the equation of motion, just by using the work energy theorem, you can get a lot of important physical insights about the motion of the system. And importantly, most of the important forces which we experience in our daily lives, like gravitational force or electromagnetic force, all these forces are conservative forces. So in a lot of the practical situations, you can apply the work energy theorem with great efficacy. And second situation where work energy theorem is particularly useful is when the path is known because the motion is constrained. A constrained motion, what we mean, are motions in which the external constrained forces act to keep the particle on a predetermined trajectory. For example, in the case of a train, the train moves only on the track, right? So the trajectory is predetermined. Or in the case of a conical pendulum, we know that the bob moves only in the circular motion, in the circular path, right? Here the length of the rod acts as the constraint parameter, so that restricts the radius of the circular motion, right? So in the case of constrained motion, we can apply the work energy theorem. Now, as a starting point, let's take a simple case, that is work done by a uniform force. So calculate the work done by a force F equal to F naught n cap, where F naught is a constant force and n cap is a unit vector in some direction. As a particle moves from initial position Ra to final position Rb along some arbitrary path. Okay. So initially the object is at point A, where the position vector with respect to some frame of reference is Ra. At the end of the motion, it reaches the final point B, where the position vector is Rb, and throughout the motion, the force acts on the object is a constant force. Its magnitude and direction both are constants. So let's see whether we are able to apply work energy theorem in this particular case. So we know that WBA is integral Ra to Rb f dot dr. Substitute for f is F naught n cap. Since this is a constant force, I can take it outside the integral. So F naught n cap dot integral Ra to Rb dr. Now you can write dr in terms of the components. So if you're following a Cartesian coordinate system, then dr has three components: the displacement along x, which is dx, displacement along y, which is dy, and displacement along z, dz. And I, j, k are the corresponding unit vectors. And the limits of the integral you can write in terms of the Cartesian coordinates x, y, and z. Okay. Now when you do this integral of dx is x, now you apply the limits. Only the limits with respect to x coordinate will be valid here. So upper limit is xb, lower limit is xa, so you get xb minus xa I cap. Similarly, you have ib minus ya j cap and zb minus za k cap, and its dot product with f dot n cap. And the term inside the bracket is nothing but Rb minus Ra. So this is Ra, this is Rb, and this vector is Rb minus Ra. So you have F naught n cap dot Rb minus Ra. Now how do you calculate the dot product? This is nothing but magnitude of first vector into magnitude of second vector into cosine of the angle between them. So from this figure, you can note that the angle between the vector Rb minus Ra and F naught is theta. So this is going to be magnitude of the unit vector, which is 1 into magnitude of this vector. This is the symbol for magnitude. So magnitude Rb minus Ra into cosine of the angle between them, which is cos theta. So if you look at this expression, you can easily make out that the work depends only on the net displacement Rb minus Ra. So it depends only on the endpoints. It doesn't actually depend on the path followed. Okay. So in such cases, you can apply the work energy theorem, and without solving the equation of motion, you can get a lot of important information. So in the next lecture, we will see some practical examples where we will be able to apply the work energy theorem very easily. Stay tuned for that. Thank you.